Today in Lab 3, we will be having a situation where a star is orbiting a black hole. In this lab, we will observe the motion of the star from the given position, mass, and time update, and determine the mass of the black hole using Newton's gravitational force and the momentum principle. The given information before the lab was the star's position, which was given on the CSV file, the star's mass, which is 1.989 times 10 to the 30 kilograms, and the time step for 1 day, which is about 86,400 seconds. Also given to us is a specific position of the black hole, which in our case is 0 in the x position and 2 times 10 to the 10th meters in the y direction. The momentum principle is also known as P equals F net delta t, where final momentum equals initial momentum plus net force times delta t. Net force is also equal to dp dt, which is the change in momentum over time. F net is also equal to F parallel plus F perpendicular, which are the two components that make up the force. We also use Newton's gravitational force. We know that the constant is equal to 6.7 times 10 to the negative Newton meter squared over kilogram squared. And knowing the previous information, we try to get the mass of the black hole. In the code, we put the black hole mass as this. Black hole mass equals the magnitude of the net force times the magnitude of the star position minus the black hole position all squared over the constant times the mass of the star. For the model settings, we initialized our code with the data we know. We added the star and the black hole, which would be in the model, along with the mass of the star, the position of the black hole, and the time that we know. We also have the position of the star, which is given in the CSV file called star data, and along with that, the first while loop is here to show the velocity of the star during its orbit around the black hole. In the second while loop, v initial and v final are found and later used to find p initial and p final, which show the momentum by multiplying the star's mass and the respective velocity. Delta v and delta p are also found knowing these needed values. As shown previously, dp dt is equal to delta p over delta t. Fnet is equal to dp dt according to the momentum principle. The direction of the momentum is defined as p hat. P hat is found by dividing the initial momentum by the magnitude of the initial momentum. The magnitude of dp dt is found by subtracting the magnitude of p final by the magnitude of p initial, then dividing everything by the change in time. dp dt parallel is equal to the change in magnitude times the p hat, the unit vector. The parallel net force is equal to the parallel change in the momentum. dp dt perpendicular is equal to dp dt minus dp dt parallel. This gives the perpendicular net force equal to dp dt perpendicular. Also added is the constant for the gravitation, which is 6.67 e to the negative 11, and also the equation to find the mass of the black hole. I shall now run my module on v-idle. So as you can see, this makes an orbit around the black hole. The yellow is the total net force, while the blue arrow is the F net perpendicular, and the black is the F net parallel. Given is also different values which are important for finding out the mass of the black hole. The given data from v-idle was the time, the magnitude of F net, the magnitude of F net parallel, the magnitude of F net perpendicular, and the mass of the black hole, which is approximately 2.7862 times 10 to the 31 kilograms. A question that we might ask is, how is Fnet different from dp dt? From the momentum principle, we know that Fnet is equal to dp dt, and the parallels and perpendiculars are equal to each other. They are calculated in different ways, which is the main difference. The gravitational force can be found through the gravitational force equation, which is right here, while dp dt is derived through the change in velocity, so dp dt equals ma. One main difference is that dp dt says how the star moves, while Fnet affects the star's motion. For this what-if question, could you tell the difference if this was the situation? The answer would be no, because the mass of the black hole would be would not have a difference if the motion of the star is unchanged and the positions from the CSV file are the same. There is no alternative gravitational force to calculate a new mass for the black hole. If there were similar paths but different points, there could be a possible new mass. There is not room for error in this lab since it's all done through VIDLE, since there was no experimental data. Overall, this lab is effective in trying to find the mass of an object from given data using the gravitational force and the momentum principle. Thank you.